Good morning, students. Today I am going to discuss some more questions from exercise 4.1. Now, question number 6 is using principle of mathematical induction, show that this result is true. Now, as we know, we can write the given statement as principal statement, right? Now, for firstly, we write for n equals to 1. What is your P1? On left hand side, we are going to take the first term, that is 1 into 2. And in right hand side, we are going to put n equals to 1. So this is 1 into 1 plus 1. Here 1 plus 2 divided by 3. Now your left hand side is 1 into 2. Answer is 2. On right hand side, we have 1 into 2 into 3. Now this 3 is cancelled. So your answer is 2. That means your result is true for n equals to 1. Second step, we assume that pk is true for some natural number k. That means you are assuming that the given result is true for n equals to k. So in this series, 1 into 2, 2 into 3 plus 3 into 4. Here we replace n with k. So this is k into k plus 1. In the same way, on the right hand side, this is k into k plus 1 into k plus 2 divided by 3. Right? Label this equation as equation number 1. Now the third step, we need to prove that pk plus 1 is true whenever pk is true. Right? Now pk plus 1. You can write the first k term from here up to here, and for the last term put n equals to k plus 1 in this term. This is going to be k plus 1 into, if you put n equals to k plus 1 here, this is going to be k plus 2, and on right hand side you replace n with k plus 1. So this is k plus 1 into k plus 2 into k plus 3 divided by 3. Right? Write your left hand side again. Now, sum of these k term, we can write this sum using equation 1 as k into k plus 1 into k plus 2 divided by 3 plus the last term as it is, that is k plus 1 into k plus 2. Now from these two terms, you can take k plus 1 and k plus 2 common, and you are left with k by 3 plus 1. Now take LCM. LCM is 3. So this is going to be k plus 3, which is equal to your right hand side. So your pk plus 1 is true whenever pk is true. The same process, if it is true for n equals to 1, you have already shown that the given result is true for n equals to 1. Now using these two steps, the result is true for 1 plus 1, that is n equals to 2. Now if it is true for n equals to 2, again using these two steps, the result will be true for n equals to 3. That means by using the principle of mathematical induction, the given result is true for all natural numbers. Next question is question number 1. Using principle of mathematical induction, show that this result is true. Now in the same way, we can write our statement as principal statement. Right? First step, for n equals to 1, that means your P1. On the left hand side, we are going to take the first term, that is 1. On right hand side, put n equals to 1. So this is 3 raised to the power 1 minus 1 divided by 2. So 2 by 2, that means left hand side and right hand side both are equals to 1. So your Pn is true for n equals to 1. Second step, we assume that pk is true for some natural number k. That means in this given result, you'll put n equals to k. So the series is 1 plus 3 square up to so on 3 raised to the power k minus 1. You put n equals to k here. In the same way, on the right hand side, this is 3 raised to the power k minus 1 divided by 2. Now, third step, we need to prove that pk plus 1 is true whenever pk is true. First, you'll write your pk plus 1. first k terms, the sum of first k term you can write from here, right? And for the k plus 1th term, you just put n equals to k plus 1 here. So this is 3 raised to the power k plus 1 minus 1. So it is going to be 3 raised to the power k. In the same way, on the right hand side, put n equals to k plus 1. So this is 3 raised to the power k plus 1 minus 1 divided by 2. Now take your left hand side again, right? Using equation number 1, the sum of these k term is equal to 3 raised to the power k minus 1 divided by 2 plus the last term 3k as it is. Next step, take LCM. So this is going to be 2 into 3 raised to the power k. Now I am rewriting this as 3 raised to the power k plus 2 into 3 raised to the power k minus 1. From these two terms, you can take 3 raised to the power k common. So you'll have 1 plus 2, that is 3. Or simply if you have a plus 2a, that is going to be 3 times a. So this is 3 times. From these two have 3 times 3 raised to the power k minus 1. Base same, power will be added. So this is 3 raised to the power k plus 1 minus 1 divided by 2, which is your right hand side. So your pk plus 1 is true whenever pk is true. Hence, by principle of mathematical induction, the given result is true for all natural numbers. Next question. Question number 3. Again an important question. Using principle of induction, show that the sum of this series is equal to 2n upon n plus 1. Right? Now, we can write the given statement as Pn. Done. First step, for n equals to 1, that means your P1. On the left hand side, you are going to write the first term, that is 1. On right hand side, you are going to put n equals to 1. So this is 2 upon 1 plus 1. So 2 by 2, answer is 1. That means your Pn is true for n equals to 1. Second step, we assume that pk is true for some natural number k. Right? Now look at the series. For the first term, you can write this as 1 upon 1. For the second term, 1 upon 1 plus 2. For the third term, 1 upon 1 plus 2 plus 3. This is nth term, 1 upon 1 plus 2 plus 3 up to so on n. If you put n equals to k, that means if you are writing the sum for the k terms, this is first term, second term, third term. For kth term, we are replacing n with k here. This is 1 upon 1 plus 2 plus 3 up to so on k. This is your kth term. And on the right hand side, again you are going to put n equals to k. So this is 2k upon k plus 1. The third step is, we need to prove that pk plus 1 is true whenever pk is true. The important step is how to write your pk plus 1. The first k term you can write from here. Done? Now for the first term you have 1 upon 1. For the second term you have 1 upon 1 plus 2. For the third term you have 1 upon 1 plus 2 plus 3. For the kth term you have 1 upon 1 plus 2 plus 3 plus k. That means for k plus 1th term you will have 1 upon 1 plus 2 plus 3 up to so on k plus 1. In the same way, replace n with k plus 1 on the right hand side. So this is 2 times k plus 1 divided by k plus 1 plus 1, that is k plus 2. So write your left hand side again. Now from equation number 1, the sum of these k terms, using equation 1, this is equals to 2k upon k plus 1 plus this last term. Now look at the series. This is 1 plus 2 plus 3 up to so on k plus 1. The given series, the series in the denominator is in AP, whose first term, I am writing here, the first term is 1. Common difference is also 1. Number of terms are k plus 1. I am talking about this term, right? The series in the denominator is in AP. The first term is 1. The common difference is also 1 and the number of terms are k plus 1. So that means you have to find the sum of k plus 1 terms which are in AP. You can simply use the formula Sn, that is number of terms divided by 2 into first plus last term, or you can also do it by n by 2 into 2a plus n minus 1 into d. So the number of terms are k plus 1 divided by 2 into first plus last term. Now here your first term is 1 and the last term is k plus 1. Right? So this is 1 plus k plus 1. This is as it is. You have k plus 1 upon k plus 2 divided by 2. Now in next step this 2 will move to numerator. Done? From these two terms you can take 2 upon k plus 1 common. So you are left with k here, and in the second term 1 upon k plus 2. Next step, take LCM. LCM will be k plus 2. So this is k into k plus 2, that is k square plus 2k, and this 1 as it is. Now you can rewrite this as k plus 1 whole square. Next, 1 factor is cancelled. So if 1 is cancelled, you are left with 2 times k plus 1 upon k plus 2, which is equal to your right hand side. So you have shown that pk plus 1 is true whenever the pk is true. So again, by using the principle of induction, the given result is true for all natural numbers.